right, November the 30th through December the 4th. Guys, really quickly, let me go back for just a second. Every question that was on your work the last time can be answered without a calculator. I only gave you the Desmos.com just in case you wanted a tool to help. But every question can be answered without a calculator. The only time you would need a calculator would be if it tells you to graph it using a graphing utility. Alright, so today we're going to model with polynomials. Our goal today is to interpret and represent relationships between two types of quantities with polynomial functions. Alright, so in our last lesson we talked about doing an open-topped box and cutting out congruent squares from each corner of the piece of the construction paper. And because we didn't get to actually do that activity, I went ahead and filled in some information. I filled in that our length was 45 7/10 and that our width was 30 5/10. And it wants us to express the dimensions of the box in terms of x. So if I were looking at our length, the length of our box would be 45 7/10 minus, remember we said we were cutting out this, so minus x here and minus x here because I don't know how much it is. So I would say our length would be 45 7/10 minus 2x. Looking at our width, our width is 30 1/2, alright? But I'm taking out x amount here and x amount here, so I would represent that by saying 30 1/2 minus 2x. And then our height, I spelled that wrong. Alright, our height, well, how tall is it? Well, it's going to be x height because it's going to be however tall that square is that you cut out. Alright, so it says write a formula for the volume of the box as a function of x and give the answer in standard form. So if you remember, volume is length times width times height. Alright, so we can just call this V of x, or the volume of x is equal to length times width times height. Alright, so I would have to multiply all of this out. Alright, so I would multiply, and it's up to you however you choose to multiply this out. But this is what our function would look like of x. By the time I multiply all of this out, I would get 4x cubed minus 152 4/10 x squared plus 1,393 85/100 x. So that's what it would look like as a function. Alright? That's how it would look like as a function. Alright, so let's look at the rest of this. Let's see. The owner of Dizzy Lizzie's, an amusement park, are studying the wait time at their most popular roller coaster. The table below shows the number of people standing in line for the roller coaster T hours after Dizzy Lizzie's opens. Alright, So obviously at 0 hours, it's not open yet, so there's nobody in line. After 1 hour, there's 75. At 1 hour, there's 75 people in line. All right, so you understand what the table's saying to us. Jalen made a scatter plot and decided that a cubic function should be used to model the data. His scatter plot and curve are shown below. All right, so cubic function is the U-shaped. All right, so he decided that that's what would make the best point. It would hit most of our points. All right. So, unfortunately, we're going to have to flip back and forth. Do you agree that the cubic polynomial function is a good model for the data? And explain. Yes, the curve passes through most of the points and seems to fit the data. If you go back and look, it doesn't hit every point exactly through the middle of the point, but it does hit the point at some point. So yes, the curve passes through most points. Alright, so we're going to say it's a good fit. What information would Dizzy Lizzies be interested in learning about from this graph? Alright, how could they determine the answer? So what might they be interested with in this graph? So looking at it, think about an amusement park. The number of people waiting in line after so many hours of the amusement park opening. Why might this be important? Maybe they might be interested in the time when the line is the longest. Alright, and then how many people are in line at that time? Why is that important? A way they can be more efficient in the way they run things. So how would they determine the answer to this? So to find this out, you could predict the number of people in line at any time during the day. All right. But if I wanted to know when the line is the longest. All right, so here's my number of hours after the park is open. All right. And then this is the number of people in line. So I could actually go and try and predict the maximum or estimate the maximum point of the graph. All right, because that would give me the time and approximately the number of people. All right, so you can estimate the maximum point from the graph. Estimate the time at which line is the longest and explain how you know. Well, let's look at this. So this is about where our line is the longest. And if I come down, these lines represent 1 hour, so it's right about 5.5 hours. All right? So the line is longest at 5.5 hours. Alright, because, now this is what we call the relative maximum. Alright? The highest part. The maximum part of the line. Because the relative maximum of the function occurs at this point. I'm looking at, that is the highest part. That is what we call the relative maximum of my function. Alright? Estimate the number of people in line at that time and explain how you know. Well, let's go back. And when it is about 5.5 hours, I'm going to come over here. And I see, okay, so I've got to figure out what they're counting by. They're counting by 25s here. So I'm between 350 and 375. It's about middle ways there. So we'll say, and notice it says estimate. That is a huge thing there, estimate. So there are roughly about 372 people. When t is equal to 5.5. When our time is 5.5. Okay? This is the relative maximum value of P. In other words, that's as high as P goes. The amount of people, that is the highest that you're going to see on our graph. Alright, number 5. Estimate the t-intercept of the function used to model this data. Alright, now notice it didn't say x, because they don't have this labeled as our x-axis. Even though it is, they have it labeled as t. So when it says estimate the t-intercept, we know it's going to intercept at 0. Then it's going to intercept over here. Alright, so that's about what? 12.5. But then look over here. Notice it intercepts again, because what happens is it comes down and it loops back up. So it's going to intercept again at 33. So the t-intercepts, whoops, are 0, 12.5, and 33. Now those are not exact without actually graphing it and putting it on a graphing calculator and doing that. Those are about what it looks like. The 0 is exact and the 33 is exact, but 12.5 may be a rough estimate. Use the t-intercepts to write a formula for the function of the number of people in line, f, after t hours. Alright? So they want to know what's going to happen here. So writing a formula for that function, let's think about this for just a second. We know that our t-intercepts are where I would get a 0 function. so we'll put that out here. That's our t. 12 and a half would be t minus 12 and a half. Because if I were to set that equal to 0, I would get 12 and a half. And then 33 would be t minus 33. Now, there's something else we need to use though. They want to know the number of people in line after so many hours. So I need to put another variable there because it's a constant that's not been determined. All right? It's something that's not been determined just yet. Use the maximum point to find the leading coefficient and explain your reasoning. Okay, so we estimated our maximum point that when t was 5 and a half, we should get about 372. All right? So we said with our function, when our hours were 5 and a half, we should get around 372. So we can plug 5 and a half in to our function and find an answer. Okay? So we're going to plug 5 and a half in to our function that we created in 6. All right? And when we do that, this is what we get. Now remember, we said C has not been determined yet. But when we plug that in, we get 1,058, and 75 C is equal to 372. Okay? So then what we would do is we would solve for C by dividing by 1,058 75 hundredths. So C is approximately 35 hundredths. The function that could model the data is then given by this. Now I've figured out what C is, so my function of my data would be alright, so we figured out what C is equal to now. And we can do that. Alright. What would be reasonable domain for your function f and y? Okay, so let's go back here for just a second. Domain. Domain is our x values here. So what would be reasonable? My graph may continue to go down and up and down and up and down. Like it may end up being something that looks like this constantly. Okay? But let's think about this for a second. Because of the situation, because we're dealing with hours, is anything past 0 on the negative side going to make sense? I can't have -1 hours of the park being open or -2 hours of the park being open. So our domain we start at 0. Alright? Then, look what happens here. What happens at what we said at 12 and a half hours? There's nobody waiting in line. So that probably means what happened? That the park has closed. So would it make sense to keep going? Well, if the park's closed, nobody's going to be in line. It says we have a negative amount of people waiting in line. That doesn't make any sense. So our domain would be like this. We said starting at 0, so x would have to be greater than or equal to 0, but less than or equal to 12 and a half. Alright, so my x would have to be somewhere between or including 0 and 12 and a half. Alright, because at 0, the park is opening. Alright. And at 12 and a half, the park is closing. This data may make sense in a completely whole other scenario, but because we're dealing with an amusement park, these are the numbers that make sense. So it says use your function to calculate the number of people in line 10 hours after the park opens. Alright, so it says if I do f of 10. So in other words, I'm going to take this function back here. 0.35 times 10 times 10 minus 12 and a half times 10 minus 33. Alright, so let's see what this would give us. So 35 hundredths times 10 is equal to 3 and a half. And 10 times 12 and a half, or 10 minus 12 and a half is negative 2 and a half. And 10 minus 33 is negative 23. So let's look. 3 and a half times 2 and a half negative times 23 negative gives us 201 people. So we're going to say the formula gives us 201 people at 10 hours. Let's go back and look at our graph and see if that makes sense. So at 10 hours, if I follow that up, well, that looks about right. Alright. Comparing the value calculated above to the actual value in the table, is your function f an accurate model for the data? Well, let's go. It says at 10 I had 180 with the actual data. So the value of the function differs by about 21. Alright? The data in the table differs by about 21 people. So we know that our model's not perfect, that our function's not perfect. But far off that it's bad. It's pretty close. Alright, so it's not perfect, but it's pretty close. It overestimates just a little bit. Use the regression feature on the graphing calculator to find a cubic function to model the data. So if we were actually to put this in a graphing calculator, this is what it would give us. Okay, that's what it would give us. Graph your function and the one generated by the graphing calculator and use the graphing calculator to complete the table. Round your answers to the nearest integers. Alright, so if we were to graph ours and graph the one that they gave us, then this is what we would end up with. We would have, our equation would give 0, the regression would be negative 24. And I'm just going to give you this data, because I don't want to spend making a huge video trying to show you on the graphing calculator. So this is what we would get. So based on the results from the table, which model was more accurate? T at 2 hours or T at 10 hours? So if I look at 2 hours, all right, 225, this is the original data, this is what we got, this is what the regression got. And here at 10 hours, they got 180, we got 201, the regression gave us 194. So which one was more accurate? T at 2 hours is more accurate. They are closer. Alright, T at 2 hours is more accurate. It was only off, ours was off by what, 3? And the calculator was off by 4. The graphing calculator was more accurate at 10 hours, but we were off by 14. Alright. Alright. Guys, you should be good. You should be able to answer any questions that you need to without the graphing calculator. I'll look and make sure if there's anything on there that needs to be given to you, I will do that. Just do your best with this. Hopefully you were able to see this and it was not extremely difficult. Hope you had a great Thanksgiving. Hope to see you guys soon.